פה, אז ליאון כבר חצי עבר ל...
אוקיי.
זה גם לא מוקלט שם.
So,
אף אחד לא יודע.
okay. Look, I continue in English just from איך קוראים לזה באנגלית? התמדה?
Consistency?
No, it's not consistency, it's persistence. Or more like, yeah. But, okay. So, you are very lucky for some reason. Either I was teaching this year extremely quickly. I don't think so, but maybe I did. Or we somehow had too many meetings,
Yes.
which we don't know.
This is the 11th.
Well, I don't know. Normally it's 13, so if we have 14, that's David, suddenly you feed it back to me. I don't know how. So do something with your microphone or earphones or something.
אני נוקם.
יכול גם אתה לענות מהקורס.
So, but that means that we will be able to finish many things that sometimes I don't. So, what are the subjects that we want to cover? So first, I think today, following where we ended last time, we discussed coherent states and explained why a coherent state is, or at least there were two things that we did without real justification. One, well, we discussed coherent state and said that the vacuum is a coherent state. And then we said that all coherent states are practically the same. They're like shifted vacuum. But then we drew something, which is this kind of x and y. And we said that this is vacuum, meaning a distribution of probability of noise around x. And if this is vacuum, then this is a coherent state alpha. So if this is alpha, so this is the vacuum, and this is the state, the coherent state alpha. Now this was not justified. I mean, what does it mean? There's no, can you really discuss a probability density of finding a value of x and y? Likely not, because you cannot measure both of them. X and y do not commute. I mean, quantum mechanically, they are operators that do not commute. The 2 is not important, the I is, which means that there is an uncertainty related to them. So to discuss a point in phase space is meaningless. So how, or under what conditions? Under what conditions can we even do this? So this is the first thing that we're going to discuss. We're going to talk about so the first subject for today will be the Wigner distribution function, which is the closest thing to a joint probability distribution you could find in quantum mechanics. So this will be the first thing that we're going to discuss, just in order to put this on more solid ground. And then we'll understand that indeed for those states it works. This kind of thinking is meaningful, but there are states where it doesn't work. Now honestly, I'll do this rather briefly. I'll define it. I'll explain some of the properties of the Wigner function, but I won't prove them all. And you will open last year's final project, which contained a long question about the Wigner distribution function. And you'll have fun to solve it. And it's not hard. And it will help you understand more about Wigner. And that is, okay. And the second thing that I want to discuss is squeezing. And here, this is like, okay, quantum squeezing is, yeah, it's something that takes vacuum and squeezes it. So, of course, we can squeeze in many directions. And to generate, so we'll discuss here first, as always, you want to understand first classically. So the operation of squeezing, so we'll discuss parametric amplification and also oscillation. Now, this part has a lot to do with nonlinear optics, which I will not teach you. So to really understand, so you will understand somewhat, like intuitively, what a parametric amplifier is and why it does what it does. But I will not explain all the nonlinear optics underlying the optical parametric amplifier and all its properties and how it is related to nonlinear optics, and what are the nonlinear interactions that generate parametric amplification. For this, you will need to take a course of nonlinear optics or take a good book and read some. But this will allow us to understand the classical meaning of squeezing, and from that we will go for a quantum generalization. We'll understand that we have like a squeezing operator and squeezed states. That's probably most of what we'll do today. Other subjects that we would like to cover during the course are, okay, so this will describe what we will understand is how squeezing operates and how the mathematics of squeezed states, but we will not understand what they are good for. And that's also something that would be helpful to see where are they useful, those squeezed states. And that has to do, well, let's see, what is the property, the unique property that they have? They have uncertainty in one quadrature, which is less than the uncertainty of nothing. So if you have, there's vacuum, it has some uncertainty in the quadratures, and these states have a lower uncertainty than this. Now, and okay, so that sounds mind-boggling. How can I generate a state which has a lower uncertainty than the uncertainty of nothing? But it is. That is the case. It's related to some special quantum correlations within the light. We'll explain which correlations exactly. It's a real quantum state. By the way, the name squeezed vacuum is misleading. Because if you ask yourself how much light is there in vacuum, how much intensity is there in vacuum, the answer is 0. In a squeezed vacuum, the answer is definitely non-zero. So squeezed vacuum is called squeezed vacuum only because it looks like this in phase space. But if you ask yourself what's the average intensity of squeezed vacuum, it's definitely non-zero. It's a real state. It contains light. It contains photons. So it's not somehow you took no photons, massaged them, and got a new no photons. No, vacuum is only one, and this squeezed state or squeezed vacuum is not magic. It's a real state composed of, that is generated by some superposition of photon numbers with some special correlation properties that generates this kind of uncertainty map. But anyway, that means that this uncertainty is real. There is something that has lower uncertainty than vacuum. And then we would like to see, so where is it useful? And we'll discuss interferometers as measurement, as precision measurement devices. Here, and an interferometer is, well, it's a really good saying, and it is correct, that in physics, everything, if there's a quantity that you want to measure precisely, turn it into an optical phase and measure it by an interferometer. That's the only truly precise measurement that we know how to do. If you want to measure distance, well, make it an optical phase and measure that phase. That's quite obvious kind of how you would do that. Have a reference arm and another arm and measure the length difference as a phase as an optical phase, and you will be able to measure it precisely. Of course, if it's time, well, to make distance time is easy. You just divide by the speed of sound. But if you want to measure mass, if you want to measure whatever it is, somehow make it an effect that affects an optical phase, and then measure that phase. This is really the only measurement that we know how to do precisely, very precisely, with precision of many digits, meaningful digits? No. Significant, better than, well, yeah, with many significant digits. Now, how many? Let's talk about the best interferometer ever built is LIGO. LIGO can measure change of length of the order of 10 to the minus 23 its length. So the length of the arm is 4 kilometers, and they can measure a shift that is 10 to the minus 23 of 4 kilometers. That gives us something of the order of 10 to the minus 19, 10 to the minus 18 meter. This is, well, do you remember how big is an atom, is a hydrogen atom? About 1 angstrom, 10 to the minus 10. Well, 8 orders of magnitude down. What about the size of the proton? Well, it's not so clear what we mean by that, but it's small, much smaller than the atom. It's about 4 or 5 orders of magnitude less than that. So 10 to the minus 14, 10 to the minus 15 is the size of the nucleus. Yes. Somebody's saying something from far away. Who called my name? Okay. Well, do you have a problem hearing me?
Well, there is a big delay.
Well,
there's little I can say.
Okay, I'll wait now, and you can ask your question.
Never mind, the delay is too big.
That's why you need to come to the class. So,
what about the measurement error? I mean, we are doing the...
okay, something about the measurement error. Well, when I say that you can measure something with the sensitivity of 10 to the minus 23 or 10 to the minus 18 meter, that means that for sure the noise is less than this, because otherwise you won't be able to tell between this and noise. So that means that LIGO, as I just told you, can measure something like the hair of a proton. If the proton grows hairs, then yeah, it has some hair. You'll be able to measure this. So something like less than 1,000 of the size of a proton when this entire 4-kilometer length is changing. That's a very important question.
How does
And
the
then,
atom
so
vibrate?
that means,
Atom moves. Even if you like take a metal piece, atom moves.
yeah, I mean, you have a huge mirror which weighs something like, it's a huge piece of glass. It's about this size.
Amazing.
It's hanging in thin air, not air actually, in vacuum.
Yeah, that's
And
fine.
right. And then it's, and by the way, you know, LIGO is measuring variations of space-time, which means that it actually, those are, what moves it? Well, it's gravitation eventually. I mean, gravitational forces. Now, but they're tiny. The only, you know, if you ask yourself, well, when the space-time expands or contracts, what expands or contracts? Do I expand or contract? Does the chair expand or contract? The answer is no. I mean, we are governed by electromagnetic forces primarily, which are 10 to the many digits, much larger than these nothing fluctuations of gravity. So no, if you this doesn't change. And actually, if all objects would have expanded and contracted together, then nobody would know that it happens. There's no way. The only thing that this happens to space, to free space-time. So that means that the mirrors should be free-falling, and then, so if they need to somehow be free-falling in space, and then then you would be able to measure the fact that the distance between them is slightly changing. But it seems to be so how do you conduct this experiment on Earth if they must be free-falling? So the answer is they must be free-falling only in the direction of the beam. So that means that, you know, if the beam goes this way, there must be no force applying to these mirrors except whatever the gravitational wave is doing. So that's why those mirrors are hanging by a thread. Really, they are threads. And they are held by a very complicated vibration isolation device to make sure that a truck moving somewhere on a road far away, because LIGO is staying positioned in places that are far away, will not interfere, and in the end. So seismic noise, all of those things need to be isolated as much as possible. And okay, and eventually, to make sure that what they measure is real and not incoming noise, they have two LIGOs. So, and that they are very far away from each other.
What it is in?
So one of them is in Washington, and the other one is in Louisiana. Washington State and Louisiana, those are really almost the most far apart corners of the United States.
Atoms have heat, they move. I'm pretty sure they move
yes.
a little more than a hair of a proton. A little more, maybe.
Well, yeah, but okay, so what you have is a huge mirror.
Yeah.
There are many atoms in it. It has an average position. This average position, well, it is indeed in such a device critical to make sure that what you're measuring is meaningful, and one of the things that you need to consider is the thermal noise of the face of the mirror. The fact that you have atoms at the real temperature means that those atoms are just, they're jumping around a little bit.
You're telling me that cooling it down and making it big is good enough?
They're not cooled down, but they are very big, and that's in this case good enough. But for the next generations of LIGO, they will most likely be cooled, and even more so, they'll probably be made out of silicon, because silicon has some, there is some temperature where its expansion at, I don't remember, something like at minus 80 or degrees, it has its expansion coefficient, its thermal coefficient flips sign, so it crosses zero. You know, for example, this happens, by the way, for water. Water contract from 0 to 4 degrees and Celsius, and at 4 degrees they start expanding again. So that's why ice floats on water, because it is colder, but it's also. So that means if you could make a mirror from water at 4 Kelvin, not 4 Kelvin, 4 degrees Celsius. If you could make a mirror from water at 4 degrees Celsius, you would have a really good mirror because it won't have any thermal fluctuations, because the thermal expansion of the medium.
Zero.
Yeah. So then, but a little bit of a problem with water is that they're liquid at that temperature, which makes it a little bit inconvenient because it's hard to take a water. Maybe you can make a mirror of water like this, but it will be hard to make it like that. But silicon also has this property. I don't remember it's which. So the next levels of LIGO are going to use silicon mirrors that are cooled to this low, because you know those people who work to measure things precisely, they have a problem. They are working against the mathematical zero, not the physical one. You know, that's the only difference between mathematicians and physicists. Physicists know what zero is, and mathematicians don't. But then there are some physicists who turn mathematicians in these kinds of measurements, which means that they're never satisfied. You know, we know how small epsilon should be. The mathematicians, they don't have a scale, so. Okay, last time I insulted the engineers, right?
Yes.
So mathematicians today, let's see who's going. Next week's chemists, after that biologists, and then. Okay, so.
The karma is a karma.
Well, the delay is not that bad now.
It's not me.
It's not me either. And then.
לא זרקת אותי ככה מחוץ למתחת למדרגות.
I understand that these are the last meetings of the course, and we could have some virats of course. But please, we're trying to teach you something here. So, so you could see where, so what we want to discuss is the quantum limits for interferometric precision and then we'll see that squeezing is what you need in order to make it better. That what you are limited by are indeed the fluctuations of one quadrature of the light that you're using in your interferometer. And if you reduce that, meaning if you squeeze the light in the interferometer, it will be better. And this is dead. Well, no. I'll do it later. And this is where squeezing helps. We'll probably waste a meeting on this. And then, what else? We'll talk a little bit about Bell inequalities and EPR. EPR, Einstein-Podolsky-Rosen paradox. I assume you know what it is, otherwise you wouldn't have been in this class. We'll discuss those. And finally, since we have time, we'll discuss the fully quantum two-level system. So if you remember, our course started by a quantum discussion of the two-level system where the field was classical. So we'll discuss what happens when the field is quantum. So we'll discuss, it's called the James-Cummings model. So it's two-level system plus quantum field, which is the James-Cummings I think, as far as I recall. And this is the case where you really think of a two-level system, but the field becomes quantum. Interesting things can happen in such a system. For example, you remember Rabi oscillations. How do you have Rabi oscillations? You shine a field on a two-level system, and it will oscillate. Now, vacuum is also a field, right? So, and then if we think about the fact that this two-level system, suppose that you have an atom excited, actually we will understand where spontaneous emission comes from. We'll show that spontaneous emission is the result of stimulation by the vacuum. And if the vacuum can stimulate emission, then what it will do? Well, you'll have a two-level system, and it will be in the excited state, and it will spontaneously emit to the ground state. And this photon that was emitted will be there, and then can be reabsorbed. This is what Rabi oscillation is. You emit, you stimulate and emit, and then reabsorb. You stimulate and emit, and then you reabsorb. This is what Rabi oscillations in a classical field is. You can do this with a single photon. If the single photon stays long enough around the atom. So you will need somehow a very closed system where the photon that is emitted doesn't just disappear, but stays around, and then it can interact with the atom for a long enough time to be reabsorbed. And then you'll have what we call vacuum Rabi oscillations, which means that you have an excited atom and nothing. It will Rabi oscillate between those two states, meaning the situation where the atom is excited and the radiation is at vacuum, and the atom is in the ground state and the radiation has just one photon. So those two things will oscillate between them. So that's the general plan. That was a long review of what we plan to do. Every time, you see, the problem is I'm talking about things that I know as opposed to other classes that I give. And then, so I don't really need the book, and I'm talking about whatever I think, and it just takes too long. And still, we're making good progress. So, let's say something about Wigner. So, yeah. So, the Wigner distribution, let me remind you, uncertainty is not a quantum problem. Uncertainty is a wave problem. Any wave, classical waves, have the uncertainty property. This is what we call Fourier relation. The fact that, if you describe some, so now classically, so we're going to talk about the Wigner distribution function. This is the subject. And we're going to start to understand this from thinking about, I don't know, a classical pulse of whatever you want. It could be sound, it could be light, it could be, I don't know, an oscillation in a string on a guitar. Now, any wave, if you have it in time, you can do a Fourier transform to describe it in, well, in K, which is, we can put here a tilde, of course, but very quickly we will lose that tilde. Integral dx e of x e to the minus ikx. 1 over square root of 2 pi, but who cares? And what you know is that if you multiply the uncertainty of E or delta x by delta k, this is something of the order of 1 or 2 pi, or in this case it's actually 2 pi. What? Of course, more than, not less. Thanks for correcting this. And this, what is the definition of delta x? Well, it's the second moment of x. So this is like really, I can integral. So this is, we look at E as if it is a weight or
State.
yeah, so we can talk about the average x is
Integral EXX.
so here we have, we take this E of x absolute value squared, because this is what, you know, we consider somehow the probability to be. And of course, we can talk about x squared like this. And then out of those two, you will generate delta x. And of course, you will do the same calculation in k to generate delta k. And you'll find the average x, which is, well, the peak. If it's a Gaussian, for example, that's where the peak is. And you'll find the width of that Gaussian. And you'll see that all of those things you know. Now, and we can do this in x and k or omega and t. Now, but here comes a problem. You know, when you read music, now you have music, what does it say when you read the notes of a song that you want to play? It tells you when to play which frequency. So, you know, what does this tell you? Well, you can never know both time and frequency because there is an uncertainty relation between. Yeah, but maybe I don't want to know it that precisely. And this is what, when we play music, so we do have a feeling of this frequency comes now and another frequency comes later. Or this k vector is here and another k vector is there. Now, of course, that means there is some uncertainty associated with it. But, so, yeah, so this, yeah, when you read notes, well, let's see. I think that maybe I'm yeah.
Yeah, but the node is not instantaneous. Yes, some length of time. יש לו nodes זה אורי בזמן.
It can. It doesn't sound really bad what I wrote here, but
יש להם רוחב בזמן, זה לא כאילו שאתה מוריד על המיטה ועכשיו נהיה אפס, חוזר לאפס.
Well, okay.
You can just tap it.
Well, yeah, but still, I mean, this is time and this is frequency. So you want to ask yourself, can I write something in this space that describes the evolution of frequency as a function of time? And then, and the answer is yes. And so let me show you. So now I want to define the Wigner distribution of x and k. Of those two, both of them. We can do the same for omega and t. Well, let's call it this. This is the integral of e of x plus x prime over 2 e star of x minus x prime over 2 e to the I k x prime dx prime. You know what? Let's do it like this. So this is a Fourier transform of what? Not intensity. It's the correlation function. It's the coherence function. So this is, if you remember, we were talking about the coherence function, which was a function of x and x prime, which was what? We wrote it like this: e of x plus x prime e star, average. Well, you see, this is the same thing. It's just, yeah, move it a bit. And by the way, you can use this to define the Wigner function just as well. It's just more convenient to use the symmetric form. So it is the coherence function is a function of two positions. Or in this case, we think of it as a position and a distance. And the Wigner function says, okay, take a Fourier transform relative to one of them, which is the distance between the 2 points. And actually, this is one of two. And then the question is, well, what is this? And we can start generating properties of this function. And I'll explain some of them. I'll state some of them. The first thing, let's calculate very quickly what is the Wigner function of a Gaussian. Okay? So let's assume, right, suppose that E of x is e to the minus x squared divided by sigma squared. So that's quick. So in that case, the Wigner of x and k is what? Integral dx prime, what? E to the minus x plus x prime over 2 squared divided by sigma squared, e to the minus the same thing. Well, let's see. Well, what will we have here? Those are all exponents, and you need to complete the square, open up. So we will have here e to the minus twice x squared divided by sigma squared. That will be out. We can take it out from here and here. And then there will be the integral dx prime of what? Let's see. E to the minus. Now, the mixed term dies, and we will have only e to the minus x prime squared divided by 4, but it's twice, so it's 2 sigma squared times e to the minus I k x prime. Well, this is just a Fourier transform of a Gaussian, which is a Gaussian. And what we will have then is indeed e to the minus 2x squared over sigma squared times e to the minus, I think it will be 2 sigma squared k squared. I don't want to use bad language, so I won't say anything about that pi.
I already know.
You know what I'm going to say?
Yeah.
Good. Too bad. Okay. Well, now, the nice thing about this is that what you see is uncertainty comes in by itself. So it means that the Wigner function of a Gaussian is a double Gaussian with a width in x and a width in k. So if this is k and this is x, so here we have the width of, well, of order sigma. There's a twice and whatever. And here there is of order 1 over sigma. And actually, the multiplication does come, it should come to be 1. So maybe...
it should come to be 2 pi. Yeah, you just divide the right side with 2 pi. It doesn't matter.
Did I make a, did I forget the 2 pi somewhere?
You gotta divide it by 2 pi.
Where did I?
transform? The right part of the equation, the right exponent is supposed to have divided by 2 pi.
This
No,
one?
not here, no. Below it. The answer should have divided by 2 pi.
Where? Here
Here.
or there?
No,
There should be a
in
2
the
pi
exponent.
in the exponent.
Yeah.
You remember it,
Yeah.
because I don't. That's fine. Good. Okay. Divided by 2 pi. Okay, very good, very good. 2 pi here.
Yeah.
Now you're happy? So am I.
Square.
Nudnik. Like this.
עם סוגריים.
עם כל הסוגריים.
זהו.
Now you're happy. Good.
עכשיו זה אומר שזה 2 פאי.
כן, זה 4, אז 2 נופל, ואז זה 2
לא,
בריבוע.
זה לא משנה. זה פשוט הוסיפה 2 חלקי סיגמה בציר ה-K. 2 פאי חלקי סיגמה בציר ה-K.
This is why I hate working with K and I prefer working with...
אני לא התעקשתי על 2 פאי, אני התעקשתי על 2 פאי. פעם זה לא משמעותי.
Okay, okay, very good, very good. So now, but what we have
משמיעים אותי כי אני
is...
צודק.
What?
משמיעים אותי כי אני צודק.
Exactly. No, no, actually you're right. It is unfortunate. And you can do this, you can start calculating all kinds of such. And so, okay, so this is nice. We can also try to calculate, I don't know, what's the Wigner function of, if I'll take e of x equals the delta, a delta function. Then this will give, you can clearly, okay, it will be just this, delta of x minus x0. So this is, it is delta of x and infinite in k. Now, and you can just plug it in here. So really, what you'll have is just a Fourier transform of a delta function, and then I can tell you, and so that's. Well, that was case 1, and that was case 2. What? Are you explaining why this is right or why this is wrong?
Why this is right.
Good.
שאני אזלזל במה שאתה כותב, שאני אתווכח על מה שאתה כותב, מה פתאום. אף פעם לא עשיתי את זה בשום קורס.
Well, okay. And by the way, what will be the Wigner function of e to the ik0x?
E to the ik0x. Delta.
Yeah,
Just like this.
yeah. That's that. And this one is x and k, and it becomes this.
Amazing.
Infinite like that. So one thing is that, in a sense, it comes out of here, because you know that delta functions are the limit of of a Gaussian that is either if it's a Gaussian that is very wide, it's actually a delta in k, and if it's a Gaussian it's very small, then it's a delta in x. Now, so those are things that are nice, and even more so, you can take another thing, and this one really makes the things interesting, and that is to take e of x equals, this is a chirp function. It's an imaginary Gaussian. So e to the I x squared over sigma squared. So this means this is something else. Okay? Now I'll explain what this is, and then we'll. So you know, this is something that has just a constant frequency. What is its frequency? K0. So this is a plane. Now what about this guy? Now here, this is called a chirp. Now first of all, mathematically it's very easy to put it in there. And you will see, first of all, let me tell you what it does in Wigner. It does this. So it becomes this one. Yeah, let me try to draw it also passing through the center. So it has, it's a delta of x minus,
equal k.
yeah, or x minus k something.
Okay, Kirsch is a weakness.
Yeah, x minus alpha k. Now, let me explain this a little bit. What is a frequency? The frequency is the rate at which you acquire phase. The frequency is how far do I need to go in x to acquire 2 pi? And the answer is 2 pi over, okay, so 1 over this. So k divided by 2 pi. Okay, well, you understand. The period, it's 1 over the period, and the period is the distance that I have to go to acquire 2 pi of phase. Now, but what if the frequency, so we can say that the frequency is the rate of phase acquiring. Now, in this case, it's simple. If I ask myself, what is the phase as a function of x here? Well, that is k0 times x. And what is the rate of acquiring phase? That's k0, which is the frequency. So now let's make a leap of thinking and say, okay, now here the phase is a purely linear function. What if it's nonlinear? That means that basically the frequency changes as a function of time. So what about here? Here the phase is quadratic. The way we wrote it. So here, this is, well, it's 2x divided by sigma squared. If I think of this as being the frequency, what would I say? The frequency changes. It starts, I don't know, negative, and it passes through 0, becomes positive. Now, this is something that's very common in sound. I mean, you can make signals like this. It's called a chirp. And okay, so this seems like Wigner catches it exactly, and actually the coefficients also get right. I mean, if this was 2 over sigma, then this slope is 2 over sigma squared. So this alpha here, it should be either 2 over sigma squared or sigma squared over 2, or with 2 pi and yeah. But the coefficients do come out right, and so you can see that somehow this thinking seems to be okay. But, so that was, so far, things seem fine. And now remember, so before we go a little bit further, and you can prove, before we go even further, let's say another few things about the Wigner function. There are several more attributes of the Wigner function that make it convenient to operate, to think of as this kind of phase space distribution. The main thing is this. This is a function of x and k. But if this is, if I think of this as a probability distribution function in 2 dimensions, then there are 2 things that should happen. You know that if you have p of x and y, and you integrate the x, you should get probability of just y, independent of x, right? So, and indeed this happens. So if you do this, dx, this will be, let's start from dk, because we so far discussed things in x. And that will be the e of x absolute value squared. So this is exactly, so this makes it feel like a probability density function. Now I'll tell you even more than this. We can do the same in if I integrate dx, then this comes out to be e tilde of k absolute value squared. So if I integrate over k, I get the intensity. If I integrate over k, I get the spectrum. Sorry, if I integrate over x, I get the spectrum. So this is the probability of finding a specific frequency. This is the probability of finding a different time, specific time or location. So this kind of behavior works for the Wigner distribution function. That's an important property. Another thing that we should say, and that is that, I defined the Wigner function over there. But I want to write it near that one, so I'm flipping the, yep. I want to write it here, near. So that was the definition of the Wigner function from the field in space. But I can start just the same from the field in frequency. So, I can think about e tilde of k. And what about this guy? Plus k prime over 2 e tilde star of k minus k prime over 2 e to the plus ik prime x. This is a function of x and k just as well. It's basically the same thing, just flip. Let's put here a minus, so this is the only difference. So this is the definition in x. The same definition works in k. And check it. It's simple to prove that those two are the same. So those two are the same definition. So you can define it from space. You can define it from the frequency domain. Well, how do you prove it? Well, you put in here. You basically put in the Fourier transform inside, and you'll have an integral dx prime, and in here you'll have an integral dx double prime, and you'll have a delta function somewhere coming in, and out of this delta function you will end up eventually with the same, what?
I have a question.
Yes.
How this Wigner function helps me understand why I know the frequency of a music note, and I know the time. When I look at the note, it's kind of a delta in time. I can look at it as delta.
Well, nearly, no. I mean, if it was a pure delta, then it wouldn't have had a frequency. You see, if I take a pure delta in time...
That was the original problem, because I know...
Wait, okay. But you have Gaussians.
So I look at it as a Gaussian?
Yeah, so actually, if you want to think about notes, then what you have is something like saying, look, during this time period, you have this frequency, and there is a window. And the longer the window that you allow is, the better accuracy you will get in the frequency. So actually, when we think about music, we should think of things like this. But indeed, so yeah, but I'll show you in a moment that things are a little bit more complicated. There are things that are happening here that are but this is what you should think of, and that's fine. I mean, if you have something that has a duration of 1 second,
so
it could be the frequency is defined.
I have enough wavelengths in 1 second, so I can figure out the specific.
And the accuracy will be 1 over a second, which is 1 hertz. So if you have, if you think about the note, and the note is 440 hertz, and you're playing it for a second, then the uncertainty is either 440 or 441. So, and that's not a big difference. But if you play that note for very short time, how short? Even shorter than 1 period, then you can't ask yourself what's the frequency. It doesn't have any frequency.
And if it's very, very short, I can look at it as a delta function in time, and then it's a straight line in the...
it's like hitting a drum.
Yeah.
Seems like...
And then... So, yeah, everything seems nice. It has the right, it's a 2-dimensional function. It gives it generates the one-dimensional probabilities correctly. So everything looks perfect. The only thing is that what I didn't prove and what the probability should be, it should be positive. Probability should be positive and normalizable to 1. This is normalizable. The total area of the Wigner function is indeed 1. I mean, if I look at so we had this, that was nice, and even we can do this integral of Wigner of x and k as a function of dx dk. This is, well, I don't know, 2 pi or 1 or something, but or 4 pi. But it is a constant. So all that is nice. The only thing is that the Wigner function can go negative. What?
Shouldn't it be 1? Why 2 pi?
Because I didn't normalize it ever. You know, all definitions here are not normalized. What?
No? Your fields aren't normalized?
I don't know what your fields are, but
I'm very organized.
So your fields are normalized correctly. You know what? Okay. Better? Now. Yeah. So you can, or let's put it like this: if those are normalized correctly, and if the definition of W is normalized correctly, then you get it 1.
We are very good mathematicians.
Yeah. But in any case, it's a constant, and you can normalize by this constant, and then everything is fine. Now, the only thing is that it can go negative, let me show you very quickly a case where it does. Okay? So suppose that I have a field which is 2 Gaussians. So something like, 2 pulses. I'll have this is t, or sorry, this would be x, and this is indeed e of x. And we have a Gaussian around x naught and another Gaussian around minus x naught. So this is e to the minus x naught squared divided by sigma squared plus e to the minus x plus x naught squared divided by sigma squared. Now the question is, what is the Wigner function in this case? And let me remind you, take a look at this definition. This definition will have, now the point is that this is a nonlinear function. When you multiply e by its conjugate somewhere else. So we're going to basically take this in a way squared. Right? And then when we multiply this function, shift it by x prime with itself shifted by minus x prime, we will get some contribution from this multiplied by itself, which is the Fourier transform, which is just a Gaussian, the standard Gaussian, shifted by to x naught. Okay? And we will have a contribution from this one by itself. This will be the Gaussian shifted to the other side. So we're going to have a Wigner function that would look like there will be a Gaussian here around x naught, and there will be a Gaussian here at minus x naught. But there's going to be a mixing term. There's going to be a mixing term that will sit in the middle. Now, it's very easy to calculate its Fourier transform, and it comes to be cosine of x. So you will have here, and now I have to do something. You will have a mixing term that sits at 0. So this is from the contribution of this one, this from the contribution of this one, and the mixing term. And then let me, let's decide that red is positive. So this entire range is positive, and this entire range is positive. And this range in the middle, it will have positive, negative, positive, negative. It goes like cosine x multiplied by some envelope of
another Gaussian?
what?
An envelope of a Gaussian?
So this would be a plus, minus, plus, minus. It goes like cosine x multiplied by some function of k, which I don't care to write. Now, the mixing term, okay, so what is this? And even more so, this is something that knows about the sign that we put here. If this was a minus sign, then instead of a cosine, this would come as a sine. So those fringes that look like interference fringes, they can be shifted if this is a plus or a minus. So yeah, it does. And there's one thing that I didn't say, and I should have, and that is that the Wigner transform is also invertible. So far I took a field and generated the Wigner function out of it. But I'm telling you that you can take the Wigner function and get out the field up to a constant phase. This is another important property. It's actually coming out here already. So you know that this, I told you, if the Wigner function is here a cosine, you know that those two Gaussian comes with a plus. And if it's a sine, then they come with a minus. But now, so this, and as I told you, you have a really good exercise where you will prove all of those rigorously, and you'll find all the 2 pi's that I missed. And it's a lot of fun, yeah. But yes. No.
שווה לעשות.
למה קוסינוס ולא סינוס? כי הרי מבחינת הציור שלך זה יותר מתאים לסינוס מאשר לקוסינוס פלאס ימנים כאילו של פלוס מינוס.
Because I don't remember if, well, first of all, don't believe this and don't believe that. But what you should believe, okay, yeah, if we want to be consistent, if I drew like that, then write here a sign. But that's not the point. Yeah. Well, the other things that I told you were all correct. It will flip from a sine to a cosine when you change the sign here. And actually, if this, you could make this complex even. So if you have your plus and I, it will shift this phase of this interference term. And as I told you, so what did we see? We saw that the Wigner function behaves reasonably when we take a delta of x, a delta of k. You can write it in a reasonable way, both in x and in k. You can get the distribution, the one-dimensional distribution functions out of this, which makes sense. And the one thing that I didn't tell you is that you can even write, you can check the following thing. Integral of the Wigner function of x and k over 2 times e to di k x, I think, dk. What is this? What? It's, well, right. It's nearly, but what will come out is this, e of x, e star of 0. Well, now comes, let's see if...
Because this multiplication should be correlation, no? No, actually, that give you correlation, that will bring back the multiplication. הראשון זה קורלציה, וזה מחזיר את זה בחזרה למכפלה מקורלציה.
Yes. So now the point is, let me try to remember whether this is the exact thing. We can look maybe here. Yeah, k over 2. Yeah, no, actually, this works. This works. מה?
הימני זה מעבר מ-x ל-k, ואז עושה אינטגרל ל-k, זה כמו מעבר מ-k לחזרה ל-x. בימני זה בעצם טרנספורם פוריה של מכפלה של שני שדות, ואז זה יהיה כמו קורלציה, ואז שעושה טרנספורם פוריה בחזרה, זה יהיה כמו מכפלה של שדות. כי זה עושה טרנספורם לקורלציה.
If you saw it that quickly, then I'm happy. And you approve on this? I need you in all my classes.
Yeah, up to a constant.
Okay, up to a constant, then it's good. Well, the main thing, the important thing is that there is a form. Okay, then that's true, but look at this. What does it say? It tells you that you know, the only thing that you don't know is the phase at 0. So this is telling you that you can take the Wigner function and reproduce from the Wigner function, if you could somehow, somebody told you what the Wigner function is, and you could retrieve the field up to an overall phase that you don't know. Which is exactly what we always do. In a sense, it seems like it is even more physical than the field itself, because the field has an overall phase that we can never measure. And so that's really nice about the Wigner function. So we have a problem. Any wave you think of, any wave function you think of, can be presented in Wigner. The Wigner is another representation. You can represent it as a field in time. You can represent it as a field in frequency. You can represent it by its Wigner function. You can represent it by its coherence function. All of those are all representations of the same thing. So if you agree that this is a good representation of the field, which is, by the way, correct up to an overall phase, it's also defined up to an overall phase. The same thing goes for the Wigner. All of those are all representations that are equivalent. If I give you the Wigner function, you can get the field out. If I give you the field, you can calculate the Wigner function. You can calculate the coherence function. You can calculate whatever you want. So the Wigner function is a nice thing. It has a lot of really good properties. The Wigner transform is a useful one. It appears to be doing things that are very much like what you expect in frequent from a space frequency distribution, with the one caveat that sometimes it can get negative.
Which means, what is the meaning of this minus? It means that
It means that it's not really a probability. It's a pseudo probability. It's a Wigner. So that means that it's a Wigner function, and you should remember that it's not really a probability.
Because this is a valid state.
Of course. It's a perfectly valid state.
So I can be in a valid state which has a Wigner function value of minus.
Mm-hmm. No, but there is one thing. Look, somehow all those minuses hide out. They disappear somehow when you integrate over either x or k.
So it doesn't interrupt finding the field because they disappear.
Right, or somehow, because the intensity is a valid function, and this one is completely positive. So those minus values, well, you caught me. What? You caught me. You got me.
כן, כי אינטגרל על K אמור לבטל אותם.
Thank you. As you can see, I'm very happy that you found it. Actually, you're right. No, I am glad that you found it, and thanks. So this is, yeah, but that means.
זה גם הגיוני, זה גם מה שאתה מצפה לראות שאתה עושה אינטגרל ב-K או ב-X.
אני שמח שזה הגיוני לך. לרוב האנשים הדברים האלה לא כל כך הגיוניים.
לפחות לפני שהם
מסליחים.
כן. So, as was correctly pointed out, we have an interference term with interference fringes, but I drew them wrong. They should be actually like this. And now,
but if you calculate the Wigner function,
so this is plus, minus, plus again. And now, and I was almost correct, so it's not, so it's actually some function of x and sine of, or cosine, aha, now it's a cosine. Of k.
לא.
minus cosine. Guys,
Oh, come on, don't be a nudnik.
but if we had calculated the Wigner function from E as a function of k, so it would be
By the way, I mean, if you...
Right?
No, think about what is the... By the way...
התחלת מ של x, עברת לוויגנר, ואז זה יצא קווים אופקיים, אבל אם היית מתחיל מ של k, אז כאילו...
You would get the same. The Wigner function would come out the same. It would. But let me remind you, what is the Fourier transform of this field? It's no longer a simple Gaussian.
Another mixture.
No, there's no mixture, but you know, the Fourier transform of a Gaussian that is shifted is like it's a modulation. So it's a modulation. So if you do this, if you ask yourself what is this E of k, E tilde of k, it is indeed the Gaussian in k, I e to the minus k squared divided by whatever it is. Yeah, I don't know. Sigma squared k squared, that part, whatever coefficients you need there, but then you will have e to the I kx naught and e to the minus I kx naught. Right?
It requires a kind of an angle.
So you'll have here a cosine. This is what's the Fourier transform of just cosine? Two deltas. And in this case, what do you have here? You don't have two deltas, you have two Gaussians. In x, so you'll have something that is like a Gaussian multiplied by cosine k x0. And then, and indeed, and you can see now that here, this cosine kx0 is somehow sitting here in the Wigner function. And by the way, if this was a minus, then indeed here would have been a minus, which would make it into a sign, and this sign would flip the phase of those guys here. What? Where minus I? I don't know what you're talking about.
זה לא פונקציה של x, זה פונקציה של x ו-k, כי יש לך גם הקבלה ב-k. זה לא שזה רץ באינסוף, זה לא קוסינוס שרץ באינסוף ב-k. זה גאוסיאן, זה מעטפה גאוסיאנית בכלי.
יש שם מעטפת, yeah. There's a Gaussian envelope over, this cosine k is correct. And there is an envelope that blocks this, and what happens now is that when you integrate across x, so across k, then this averages out in nothing. It's gone to zero, so all you get is those two Gaussians here and here, and when you integrate like that, well, you recover this guy. So
קוסינוס עדיין אבל היה מוזר, מה קורה בקצוות של הגאוסיאן?
What?
אני אעבור אחר כך, יש משהו...
You will calculate it by yourself. I've had enough. But okay. So then that was about the Wigner function. Now let's say something quantum about it. Now the Wigner, that's the point. The Wigner function can be you can take any wave function. It can be a sound wave. It can be an electromagnetic wave. It can be whatever you want. And we can. So now, so here comes the point. Remember that what is the wave function as a. We can write the wave function in X representation for the ground state of a harmonic potential. Well, what is that? That's what it is. So this is like, and we can write and we just, from all of what we did so far, you can immediately tell what is the Wigner function of that one. And this one is, okay, or let me say this. If the Wigner function is fully positive, just as we had with the simple Gaussian, then you can think of it as a real probability distribution function. The only problem is when you have Wigner functions with a negative value, then things become really, you cannot think about probabilities anymore. Now that means that the ground state of a harmonic oscillator is, in a sense, it looks like, in terms of the Wigner function, it's fine. Because its Wigner function is just this. I mean, that's what. So when I plot this plot, put a Gaussian here, what I am really plotting, or the only thing that I can plot, is the Wigner distribution of that state. And if you take a coherent state, which means shift this, then you'll get that. And you know that this evolves in time, and it does this. So this is, yeah. So in that sense, this is vacuum, and this is alpha. And all of those are fine, because they are just Gaussians, and Gaussians have a fully positive Wigner function. But the question comes, what happens when we start thinking about other states? And what other states can we think of? So let's think of a single photon state. So I'm going to tell you, I'm going to take psi, function of x. We know this. What is the wave function of a single photon? Well, that's the Hermite polynomial 1 of x e to the minus x squared divided by some sigma squared. Or, in other words, it's this function. It looks like this, and like this, and like that. Yeah, this is x. This is psi 1 of x. Well, you remember, if I had two Gaussians with a sign between them, I started having negative stuff. This is really like you have two peaks with a sign between them. Something is going to go different. And then you will have a Wigner function in this case that looks like this. X and P. It will be positive in the outside. We'll have a hole, a negative hole in the middle. Yeah.
You can use the Wigner function from x and p in the same way
So
like you use x and k?
in a sense, yes, because x and p and x and k are very similar. So let me remind you. After all, p and k are almost the same up to an h bar. So, or no, k equals p divided by h bar. Yes. So really, what I mean is, if we want to talk about x and p, then I would write it like this.
Basically the same.
Yeah, but that would mean integrate dx prime psi of x plus x prime over 2 psi star of x minus x prime over 2 times e to the I px prime over h bar. And maybe there's a normalization of 1 over 2 pi h bar, but okay, so and this, so this minus now, and let me tell you a little bit more. You know, these things we can measure. We can measure. Now, let me try to explain here. did it go? Yeah. So I can measure psi of x, absolute value squared. What is this? This is measurable. This is the probability of finding x. What does it mean? It means do 1,000 measurements of x and write the probability of having different values of x. So this is asking if this is like you know, what. So if we think about a standard harmonic oscillator, it's simple. Where is that oscillator? You'll find it sitting in a Gaussian around the center. I can do the same for P. Well, and that would be the probability of finding the momentum P.
How do you measure P? You need to measure.
Well, you can measure momentum.
You usually measure the position, and then you find the momentum. No.
Well, no, I mean, I can. It seems like you think in real space. So you don't see how it's clear to you that I can look at the oscillator and see where it is, so I measure x. But how do I measure P? But, well, the answer is you wait half a cycle and P becomes x, and then you measure x. But, you can, or if we go back to what are x and p in field, when we think about the electric field, after all,
A dagger or A minus A dagger.
Right.
Yeah.
Those are the quadratures. So that means that I can, this is to ask, make a measurement of quadrature x, make it 1,000 times, prepare the state again and again and again, and then measure the quadrature x, see what value you got, and then draw the probability distribution of having the values x, or the probability distribution of having the quadrature y. Now you cannot measure both of them, but you can measure one of them, do 1,000 measurements of this, and generate this probability density. And now, can you recover from those measurements the Wigner function? This is like tomography. This is called Wigner tomography, because this is, what are we doing? This is like, in X-ray, you get a projection through your body. And all of your bones are projected onto the film that is taking them. And then what do they do in CT? They take many projections like this from many directions and recover the three-dimensional object that generated them. Now we can do the same here. Look, I can project it along P and get the probability of x. I can project it along x and get the probability of P. And I can project it actually in any other direction, because if you remember a quadrature, you can just talk about a generalized quadrature. We can talk about A plus A dagger, we can talk about A minus A dagger, and we can talk about A plus e to the I theta A dagger. And then theta will actually mean along which direction am I projecting. Now clearly when you project along any direction you want, that's the point. When you project about any direction you want, any theta you want, you will get something that looks like like this, the probability of that, which looks like this h1 of x absolute value squared times e to the minus x squared divided by sigma squared times 2. It looks like, forget about what I'm writing here. It just looks like this.
באופן טבעי אתה פשוט תקבל אינטגרל לפי הזווית של 90 מעלות.
Now think about that. What is the problem? What do you see? Well, everything makes sense. I mean, look, if I integrate along P, then the fact that I get plus something here and plus something here, that's okay. But the fact is that when I integrate here along here, I get 0.
Not minus.
Okay? I get 0. But if I get 0, the only possibility that it means, if everything is positive, then only thing that you can have along this line is 0. Right? If I project here and I get this, then if this was a purely positive thing, then all you could have along the x equals 0 line must be 0 everywhere. Because whatever positive can never be cancelled. If you have anything positive in there, it will never be cancelled. Now, but surprisingly, that would mean that when you integrate along this line, there's no way you could get a 0 in the center. But you do. I mean, you get this kind of feature. No matter which way you integrate, you can integrate along this, you get this. Well, that you would say, well, that maybe makes sense, because then I think that maybe I have something like that. Right? And then it will be fine. But then I do the same measurement along this direction, and I get again this double peak. Then I would say, well, wait, then that means that I have something like this. They could never agree. If you make such two measurements, and of course if you make it from every direction and try to reconstruct the two-dimensional object that you have here, it must have a negative in the center. Which means that you can really, the Wigner function is a measurable quantity. You can measure it by doing measurements of x or p, or when we talk about the quadratures, measuring the quadratures in different angles. You can reconstruct the Wigner function, and you can see that it must have a negative part in the center. You must put it there, because otherwise you will never get this 0 here, no matter on which angle you look. So yeah, I'm sorry about the mess here. But, so how many measurements you need? That's a good question. There's there's a huge amount of work on Wigner tomography, which I don't remember, and I think we should stop about this here. Yes, but well, then the answer is, of course. So everything we said right so far was ideal. You know, we assume that the no experimental error, things like this. But and of course, when you have a really complicated function, reconstructing the Wigner function is not so easy. Let me say it like this: we measure the Wigner functions of reasonably behaved wave functions. Okay? To measure the Wigner function of a coherent state is easy. To measure the Wigner function of 1 photon, 2 photon, 3, that could still be okay. Nobody measured the Wigner function of 100 photons, of n equals 100.
Because it has so many holes in different
Yeah,
places.
it looks like a huge. It is symmetric. It's spherically symmetric. It has many positive, negative. It has a center and a ring. It flips sign many times in there, and yeah, it's hard to reconstruct. So we want to talk about squeezing. So first, I want to talk about parametric amplification and oscillation. Now, Okay. So let me tell you that you know, all of you know parametric amplification very, very well. And you have been using it for something like your age minus 5 years or so, approximately. So you discovered parametric amplification at the age of 5, or whenever it was the first time that you could swing yourself on a swing. When you sit on a swing and now you want to start your swinging yourself, how can this be? So yeah, well, and then, but why should it work? I mean, yeah. Give me, הבו לי נקודת משען ואזיז את כדור הארץ. איפה נקודת המשען? So, okay, yeah. So now, honestly, this problem is a little bit more complicated than I'm going to describe it. And the beginning, suppose that you sit on the swing, you can't touch the ground, it is sitting like it's not moving. How do you start? The answer is the very first part is indeed by rotating yourself. And then it has to do with conservation of angular momentum. Because when you rotate yourself, the entire system has some angular momentum, total angular momentum to it. So then the swing will start rotating the opposite direction. And now if you do this, if you rotate yourself in a way that is at a frequency that is related to the the eigen frequency of the swing, it will start the oscillation. But this is not what you use in order to keep the swinging, and this is something else. So now let's think that we already started swinging. You know how to amplify it, right? When you have some form, a little bit of a swing, you do something in order to keep it. What is that? Whenever you're at the end of the swing, what do? You pull with your hands and you do something with your legs. And it has to be synchronized with the swing. It needs to happen at the edge of the transfer. And then you run away to the other side. And basically on the other side, if you could, you would do the same thing in the opposite way again. Now, what is that? Actually, what you're doing is you're lifting yourself up a little bit, or it's like making the string shorter. So, and what I want to say is that suppose now that what we have, I have a.
So you're increasing the frequency to make the wave shorter?
You're moving
yes.
the center of gravity away, so
you're right. Oh, this is you're running ahead a little bit, and it is related to. So what we're doing is we are. Suppose that I'm making the length be a function of time, or I'm lifting. And as you said, it's just like making the frequency function of time, because that is just the square root of the length divided by g. And if the length is a function of time, but what it means, remember, what we're doing is not a large change. So what we're doing is we're making this be the original frequency plus some, I don't know, some small function which is periodic. Some, I don't know, so that would be alpha times cosine delta t. Now, first of all, you can understand now why it's called a parametric interaction. Because you're interacting with the system by changing one of its parameters. You're changing the frequency of the system. And as I told you, if you just sit here and now change the length of the swing, well, nothing will happen. You'll go up and down, up and down, up and down. That's it. I mean, it won't start a swing.
Because it's already zero.
Yeah, I mean, it's zero, and it won't, but it can amplify. It can amplify a swing, and let us understand how. So first of all, in order for this to amplify the swing, there is a pure relation between the frequency that you go up and down and the frequency of the swing itself, the average frequency of the swing. And by the way, it has to be exactly twice.
And this is the reason why we do it at a specific point.
Yes. Now, and this is called, when this happens, when the drive frequency, let's call this omega drive, equals twice the natural frequency of the swing, then you are in parametric resonance. And you will have amplification. But here it comes, so let's first understand what's the logic of it. Well, if you think about this, you swing with the swing, you can come to the edge, and you pull. You're pulling yourself up. What are you doing? You're using your muscles to give yourself more potential energy than you have. The swing gave you its energy and made it into potential energy, and you added. You said, okay, great, I'll use a little bit more. Then you start falling from a higher location. You will reach down the bottom with a faster speed. You'll have more kinetic energy when you pass through the center, and then if you just do nothing, you will reach a higher point in the next time. Now, pull yourself up again, and you'll increase the oscillation. But notice, it is important, not only that you do it at the right frequency, which is twice the original frequency, but also that you do it at the right phase. Meaning, I can do the same, I can lift myself up, not whenever I'm at the end, but every time that I pass through the center. Right? Every time there, I'll lift myself up. What will I do?
Nothing.
No, but I'll get less potential energy in the end. I'll de-amplify. The speed will not change. I won't change the speed. But the question is, suppose now, think about it like this. What? Okay, it's not just for, it's not momentarily, it's for you raise yourself up while you are at the end. During the time that you are transferring through here, you give yourself more, and then here you actually allow yourself to fall more. So every time it will transfer into kinetic energy. Now if you do the opposite, meaning whenever you are here, you make the string longer. So think about it in the other way.
יש פה כוחות נוספים, כי כשאתה נמצא בתחתית יש לך איזושהי מהירות, ואם אתה מגביה את עצמך אז כן קיבלת אנרגיה נוספת פוטנציאלית.
So think about it as only...
בגלל הפגיעה של החוט אחר כך אתה מאבד אנרגיה, ואז...
נכון.
כן, כי כשאתה קופץ ואת מתקדם, אז זה לעומת כשאתה עושה את זה בשיא הגובה, אתה אין... החוט לא נמתח בזה.
But that means, so think about it like that. If I was, and this is something that takes time to learn when you're young, and that is that you need to do something that is synchronized with the string, and it has to be pulling up. If you do the opposite, you hold it down, and when you are here, you just let it go, then obviously you will be doing the opposite, and you will be slowing yourself down. So now a parametric drive will amplify what goes, the oscillation that is operating at cosine omega naught t. This will be amplified.
אבי, ככה התחילה לך קריירה בפיזיקה?
What?
ככה התחילה לך קריירה
That's how your career in physics started. So if it's what? So if you are oscillating as a cosine, you will be amplified. But if you're oscillating as a sine relative to what? Relative to this, to the drive. So you will be de-amplified. Now, so I think that, or let's plot it for a moment. So here is the drive frequency is twice. So this is the drive frequency. Now we are oscillating at, if this is a cosine oscillation, then it will look like this. By the way, it works the same for a minus cosine, right? And then indeed, you know, whenever you're pulling up, for example, if the blue is pulling up, if you're pulling up when you're here and when you're here, and you're releasing down when you're crossing through the center, then this is okay. And of course, this works the same for these guys. Sorry. So positive cosine or negative cosine, they are both amplified. But if you have a sine function, then the only difference, where's the green stuff? A sine function, the problem with it is that it does exactly opposite. So if it was a sine, so here you're at maximum, and here, yeah, and here, and so on. And now, so this is going down. And why? Because, well, I think it's clear. That means that, for example, if you have this one is de-amplified and this one, the other one, too many colors. Let's go back to black. There's a song like this, but so this one is, the red one is amplified. So the sine, and this is relative to what? The drive defines what is a sine and what is a cosine. Well, what it means is that if you have a general oscillation, so what you have a method to either amplify or de-amplify an oscillation depending on its phase. So this is a phase-dependent amplifier. It can be an amplifier, it can be a de-amplifier, and it depends on what you have. So if you have a function, which is, I don't know, some e of t, which equals some x times cosine omega naught t, plus y times sine omega naught t, and you let it interact with a parametric drive for a while.
So you can measure the phase by seeing if you is increasing or decreasing the total energy?
That's true, yes. Or at least you can measure the quadrature by doing that. It's not that you measure the phase, but you can measure which quadrature you're in. So if you take this, if this is what you have at the input, and you let it interact with the parametric drive for a while, then x will be amplified, so x will be multiplied by some gain factor that depends on the duration of interaction that you had with the parametric drive and how strong it is. How strong is the parametric drive? And y will be actually diminished by the same thing. And indeed, so look at this. So this is what a parametric amplifier does. You go through a medium where you interact with the drive for a certain time. Now actually in optics it's distance, because you have light entering a nonlinear medium which is driven by some pump field, which means that inside, well, what happens when we go inside? Well, we drive. What do we feel? We feel the response of the matter. Or now things become a little bit, you know what, I'll explain a little bit more about the optics for a moment, but for now just accept this as a black box. You enter a crystal, you pass through it for a while, and then you get out. If there is a parametric interaction in there, if there is some parametric drive that does this as you propagate through the fiber or the nonlinear crystal or whatever it is, then you will be either your cosine component will be amplified and your sine component will be de-amplified, depending on what defines what is x and what is y, the drive. The drive. Now let's say a little bit about how this happens in the nonlinear optics part of it. How does this happen indeed? The answer is the following way. You can have, you know that if we think about k, okay, let's think about this not in time and frequency, but in k and propagation. Now the k vector in a medium depends on the index of refraction, right? So the k is omega times 2 pi divided by c, and c is the frequency, the wave velocity inside the medium, and this depends on the index of refraction. Now, if the index of refraction depends, now let's think what happens if the index of refraction changes in time. If the index of refraction changes in time, and we'll soon understand how, then what you will have is exactly this. It would be like you're coming with a clean frequency, but the k vector changes in time. It's like becoming faster and slower and faster and slower and faster and slower. You have a parametric resonance which we described in time happening in space as you propagate in space. This propagation, suppose that you find high index, low index, high index, low index, high index, low index. Very small amount. Now, what can change the index of refraction like this? The answer is another way, because there's what we call a Kerr effect. Kerr effect means that the index of refraction, you know of the index of refraction as just being a number. Well, you know, the index of refraction of glass is 1.5. Well, to be honest, it's not really 1.5. It depends on frequency. For some frequencies, it's 1, though it has some dispersion, and it's not exactly constant, and different frequencies have different index of refraction. That's linear, and that's not a big deal. But also, when you shine a very strong light into glass, the index of refraction changes. Meaning, if I shine a strong field into glass, and then pass a weak field in some other frequency and measure the index of refraction, I'll get a different number. It will be 1.5 plus something. And this something depends on the intensity of the drive field that we put in. But, yes, definitely. You can generate parametric interactions in many ways. Nobody said that it must be invoked optically. Why do I think optically? Because I want the frequency of the drive to be twice the frequency, the natural frequency. And if the natural frequency is optical, then I don't know how to generate something at twice an optical frequency with electronic means. But definitely, if you want to think about parametric interactions, wherever it is, yes. I mean, if you have an electronic oscillator, for example, take an electronic oscillator like an RLC circuit. Now, change the capacitance as the function of time at twice the make small changes at twice the natural frequency of the total circuit. If you do this with a strong enough drive, you'll generate oscillation from nothing. So then, we can understand, well, approximately from this thinking of the swing in the playground, how a parametric drive at twice the frequency can somehow generate gain for the fundamental frequency at the right phase. But what does this do? It takes any point. So now still we're thinking classically. If I'm sitting at point x, y. When I go through a parametric amplifier, I'm just mapping it to a new point where at x times g and at y divided by g. I'm taking this function, this point xy, to the new point, which is x times g, y divided by g. Now let's make it like... What does it do to a distribution?
The volume stays the same.
The total volume stays the same, and it will take a distribution that looks round and squeeze it. What will it do? So it will take maybe this distribution. It will make it into this distribution. Let's make everything here. Oh no, that was right. But let's make everything here red, so that we know. So this one was x and y, and this is x times g, y divided by g. Now, look. If you remember, well, the phase space distribution is not constant. It's constantly rotating, right? Every point in phase space is constantly rotating around. By the way, it is rotating around also in this picture, but we have the drive, which is exactly at twice the frequency, so it's like constantly. What does it do? Whenever, I mean, you reach every point here is just every time, every round, you stretch a little bit here and you squeeze a little bit there. And you do it a long time, so all those are stretched here and all those are squeezed. But, okay, so a parametric amplifier conserves the total area of so it conserves the total area of the distribution. Now we're thinking still classical distribution of anything, and it will squeeze it.
Also preserve the interval, right? Like the actual
Yes.
numbers. It's basically just.
By the way, it
changing
doesn't.
the space, the
It
phase
doesn't conserve the energy. It does not conserve energy. It does give energy to the problem. Let's think about this. You know, suppose, let's think for a moment that all you had was a little cosine oscillation and no sine oscillation at all. This one will be amplified, and the sine oscillation will remain 0. It was 0 and it remains 0. So the total energy was increased because you're adding energy to the cosine term, and the point is that the amount of energy that you can take out of the y term is limited. But the amount of energy that you can give to the x term is unlimited. So you're definitely you're driving energy into the system. Where does it come from? From your hands. You're lifting yourself up. You're doing work. The drive is generating work. Nobody said it's a problem. It's a fact. No, that's not up to a constant because well, you can redefine the constant every stage, but no. Exactly. A constant is something that you define only once.
Basically what I'm saying, that it doesn't just change how we look at the space.
Yes, but it's not. No, well, remember, energy is x squared plus y squared, and you can see that with this is not equal x squared times g squared plus y squared divided by g squared, right? So yeah, so that means that the energy is not preserved. The area, it is true that the uncertainty area, the total uncertainty area is preserved. And even more so, if you have a parametric amplifier with a very large gain, I don't want to say infinite, but very large gain, then this means that the contribution that you see will come mainly from x. The y part will be effectively 0. So if you measure the intensity after a large parametric gain, you will be measuring the intensity of the input quadrature x, how much you had in x at the input. So a parametric amplifier, so that's what's good about the parametric amplifier. It conserves the uncertainty area, and it amplifies just one quadrature, not both of them. So if you remember, if you try to measure both quadratures, you cannot. There's no way to do this. But the parametric amplifier doesn't try to do that. It amplifies only one. So then if you measure the output of a parametric amplifier with strong gain, you're measuring just one quadrature. So that is a way to measure a quadrature. What do? You take a parametric drive. You take this as an input. You connect it to a parametric amplifier which amplifies one quadrature, and you see how much you get out. If you get out 0, then you had nothing at that quadrature at the input. If you get a lot, you had a lot of that quadrature at the input. And if this parametric amplifier is ideal, and conceptually it can be ideal, then you will be measuring just one quadrature by doing this. So this is a way, another way, to do a homodyne measurement. By the way, you remember homodyne is multiplying by the local oscillator. And what does it give you? Parametric gain. Why? Because you have nonlinearity coming from the detectors themselves. Okay, so now, we saw so what does a parametric amplifier do? It takes x and makes it x times g, or let me replace it and write x times e to the g, small g. Well, this is just, it's convenient. and it takes y and transforms it into y divided by g, and the definition of x and y is from or it's y e to the minus g. And now comes the point, what about quantum mechanically? Everything, it's just the same. I mean, this is, what does it tell you? If you have an oscillation, a cosine oscillation, it will be amplified. Is there a cosine oscillation in the vacuum? Yes, there is. We calculated it. It's noisy. On average, it's 0, but it has a probability of being anything between 0 and plus minus half a photon.
But you have a frequency level.
But let's think about just one frequency. I have just the drive defines a specific frequency. Okay. So right now we're looking at that, and for that frequency which the drive interacts with, it will amplify that from the vacuum. And now, so we have this problem that, you know, x squared is non-zero for the vacuum and y squared is non-zero for the vacuum, but somehow x squared plus y squared, which is the total energy, is 0. Well, that's because those x and y don't commute, so that's how you can get this magic happening. But still, because those are not really classical numbers, they are operators, and we are measuring. But still, what will a parametric amplifier do? It will take x out, will be x in times e to the g. And y out will be y in times e to the minus g. This is, and it's correct for operators as it is for classical fields. And now I can say, okay, but if you remember, A is x plus iy. So A in is x in plus iy in. And that means that I can write what is A out, coming out of there. Well, that is x in e to the g plus I, y in e to the minus g. Let me do a little bit of, I want to display it. Now, if you remember, x in, what is it? It's A in plus A dagger in. Forget about the halves. Times e to the g. And this is plus I, what? Y is A minus A dagger divided by, well, you know what, I'll put here a half. Here I'll put 2i. Now it becomes important. Times this e to the minus g. Well, and the I goes away. And then you can see that I have A. What? Yeah, it doesn't matter. You want to kill the half?
No.
Probably better. No, I don't. I need the half. I really need the half because then I'll have A in. No, that's. No, this is okay. So let's see. We have A in times half e to the g plus half e to the minus g, which is hyperbolic cosine g. And I have plus A in dagger times e to the g divided by half minus e to the minus g. So this is hyperbolic sine of g. Have you heard about this transformation? Do you know that it has a name?
Yes.
No.
It's a Bogolyubov transformation. Bogolyubov. Physicists names are designed to break teeth. Okay, but this part is, the fact that this is a Bogoliubov transformation is not critical. I mean, we're not going to go deeply, that's as far as we're going, and if you don't know the name, it's fine, because you saw it already. That means that you have somehow, if you remember, we already had things like this, when you had you had some operators coming in to a beam splitter, and operators coming out. And you had here, this was A plus B, and this was A minus B. So those kinds of things that you have operators that are coming in and operators that are coming out, and they are mixing each other. This you already saw. And this means that the parametric amplifier does something similar. But it somehow mixes A with A dagger. It makes a creation operator that is a mixture of creation and annihilation. Surprising. What does it mean? Okay. So we will look, but you look at this and it looks complicated, and you say, what is this? But this part, it makes sense. I mean, this part we understood from the physics of it, because the parametric amplifier, this is really what it does. It amplifies one quadrature and de-amplifies the other. And somehow this has a complicated implication about the creation and annihilation operators of this. This will be the subject of next week. We will look at what this does quantum mechanically. We will do some quantum calculations, real quantum calculations of calculating, well, what happens, I put in vacuum, I put it through a parametric amplifier, I get a squeezed vacuum. What is the uncertainty, really, the quantum uncertainty calculated of X? What is it of Y? What is it, we'll start doing all kinds of things using this. But remember the physics, because the physics is here. All the physics is done here. Yes, so the fact that we amplified one quadrature and de-amplified the other by using a parametric, by interacting with a parametric drive. Now's a good place to stop. If you have questions, ask. And if not, you have 20 minutes until you don't meet Leon. Because today he's giving a lecture somewhere, so he can't give a lecture at two places at the same time. What? Yeah.
אני יכול לגרום שלא עלי בכלל הריסה. תמיד יש לי הריסה כלשהי, ואני יכול רק למזער אותה. יש לי G1 שאני מזער אותה, כי יש קוסינוס היפרבולי.
No, actually, if you look, both of them are increasing, and it seems counterintuitive. This is exponentially growing. If G is large, this one's exponentially growing, and this one is exponentially growing. And even, just a second, if you look at this, if you think about what happens at a very large gain, it's like doing A in plus A dagger in. You have an annihilation operator at the output that is connected to the input quadrature, just one quadrature of the input, which we just said. This quadrature that is amplified is going to be somehow inscribed completely into the output. Now it is, what does it mean? But I mean, how can you have an annihilation operator that is actually an equal mixture of annihilation and creation? How is that an annihilation, a creation operator? The surprising thing is that it is. If you take, if you calculate now the commutation relation of A out and A dagger out, well, I mean, there is this transformation. You need to do the calculation and check what turns out. It will be 1. So this transformation preserves the commutators, which means that these operators, they're okay. I mean, I don't know what they do mathematically, And the theoreticians, now I insult theoreticians, okay? So now is the time that so, you know, for the theoreticians, they don't care about what this means physically. If the commutator is fine, then everything's fine. The fact that the commutator, that the Bogolyubov transformation preserved the commutation relation is what tells you that this transformation can be physical. It does not. This is a valid annihilation creation operator just as this one, because you can do a transformation from one to the other which preserves all the commutation relations that you need. Okay. I stop. I mean, those of you who have questions, I want to ask them, I'll stay, but you are all free to go. Don't. Okay. No more questions.
מה שרציתי להגיד שם, וחשבתי קשות, להגיד שעשו את המעבר